So let's start. Okay, so we introduce this equivalency first. Next thing what we have to do is introduce the topology. Topology, you know, of course, topology, also topological relations is a closeness. I mean, so F, we have a space of smooth functions, like we have. This is X and U, yeah? They're all smooth functions, and we have to have topology. What does it mean, topology? Oh, then you heard this in many contexts. So, but this context is the topological space. We have to have the basis of open sets. So basis of open sets is in this space is defined this way. We say that something is close to some other thing if this is close with derivatives, with high derivatives. So you see, this is the huge topology. It's the most rich topology. In fact, I know maybe there is somewhere, maybe some of you introduced the more rich topology, but that's a very rich topology. It's called Whitney topology. Husser Whitney was a mathematician who was on the basis of the singularity theory. And then you see in this topology, these two graphs of functions are very close. That's a close, very close, very close. But this one are very far away. These are very, very far away. Why? Because you see here something, some bump. Because there is, you know, if you want to find a neighborhood, then the derivatives of here are huge. So this function is very far from this function. Of course, values are close. They are close, but derivatives are very far away. Yeah, if in this case, no, they are very close. Yeah, because they are on their distances of that number, nothing else. All derivatives are zero. I mean, that's if you consider the difference of these two functions, then there's a constant function which was the derivatives are zero, or the same. You understand? Only this interval is a distance. But here, the interval, of course, but the derivatives are very different. Very different. So this is this topology, you know. In this topology, if you consider the convergence is on the compact sets. So that's for if someone would like to ask questions, so please. And so we have topology, and now we have a question: if close are equivalent, if you have something which is close to something else, it's a question: is equivalent or not? Some people very close. If they are too close, then they are finally equivalent because they form the couple or something. But it's, of course, that's different. Yeah, and then the next very important notion is structural stability. Stability is something that if you perturb a bit object, then it still have the same property like before, only changed something which is not important, not so important. So up to equivalency, up to adding something which is not changing the important features of the system. So this is just what is definition of stability, of structural stability. Structural stability. F is called stable if for every F tilde, which is close to F. F tilde is equivalent to F. F tilde, which is close to F, that means that belongs to some open neighborhood in this topology. So if F is stable for every F tilde, which is close to F, so with every F tilde from some open neighborhood, they are equivalent. And then there's a question, example here, which is not equivalent. This is not equivalent. It's not stable. You see, this one is not stable. Very small perturbation, needs give this one or that, which are not equivalent to that. So then, of course, this function, this object is not stable. And now I present you very beautiful theorem, one of the most beautiful theorems of mathematics, which to prove I usually needed 60 hours, 2 semesters of teaching. But it's very nicely to formulate it, because it's not so complicated to formulate. If you have R less than or equal, this was classically formulated this way. If you have less than 4 parameters, R is less than equal to 4, you see? R is less than equal to 4. Then there exists an open and dense subset of all smooth potentials, such that if you take f from this subset, then in the neighborhood of any point of this f is equivalent to one from the list of stable normal forms. And this stable normal forms is 7. 7. You see, it was 1, 2, 3, and then 7. You see, and someone say, "Wow, these are polynomials." What is this? This is just the great achievement of this theorem. These are polynomials, because any special functions or anything is equivalent to that polynomial. So polynomials are fundamental in this theory. So you see, there is only 7 if you have 4 parameters. Why 4 parameters? Because there's a space-time. It was formulated like that by René Thom. The space-time was 4 parameters. But of course, this finite list these are like physical particles. Some roots, there's only all functions are built of 7 roots, almost all. If you remove very tiny set, because open and dense set. This is f star is open and dense. So if you close your eyes and you choose one function from f, you always choose outside of this set. You always choose from this set, f star. But never take from this pathological set, because this is infinitely codimension set. Anyway, measure problem is not existing here, because this is, of course, only because this is much more is measure 0 than normally measure terror is 0. 0. This is very, very high 0. And then you see, and now we have these potentials, and then the catastrophe theory or singularity theory use this for modeling many phenomena. It depends on the parameters. So these are parameters which you have here. This is a beautiful term. And then you calculate this stationary set, this bifurcation sets. How they look like? They look like that. You see, the set of catastrophe points, sigma f, or singularity set of, how do you prefer? So the fault, first one has a fault. So this is that one. Fault, you see? Fault. If you calculate this set of bifurcation points, this is fault, this is cusp, this is swallowtail. Because the form of bifurcation set is like that. And then fault is there, look like that, in 3 dimensions. A cusp is there, a swallowtail is like that. It's calculated. These are stable. These are not possible to spoil it. And then there are two umbilics, hyperbolic umbilic and elliptic umbilic. Very beautiful sets. And you see that maybe some complication is there, but this complication is a structure which is stable structure. Of course, if you perturb these functions down there, which were in the list, doesn't matter. These sets will be the same always. Okay, so how to calculate that? Very easy. You have the first one, the cusp. You calculate. I have no time to calculate now, but because I have some more applications. But if you consider this function, which is the cusp, written cusp. So f on x u1 u2 equal x to power 4 plus u1 x squared plus u2x. Then first what you calculate is f prime on x u equals 0. What is this? No, this is of course 4x cubed plus 2u1x plus u2 equals 0. And this is just the surface, this surface, given by this equation, f prime equals 0, this one. So then this surface over these parameters u1, u2 has such folding starting at some point. And then this folding means that at each point of these parameters u1, u2, you have these potential functions like that. If you go this way, then you go this way. So this is a kind of constant. I mean, normally in computer I would go, and then you go this. But now I just make a photo. And then but for swallowtail in this 3 dimensions, which I was not able to, you remember, I was not, but I did a photo in my brain. I calculated that and I did a photo. So what is this? If you are here, then you have this. If you are here, you have this. If you are here, you have this. And so on. If you pass through this surface, there is the very important change. If you pass through that surface, it looks like, we call it swallowtail. So that means that, you see, if you're passing through here, or you see, then you get inflection point. This maximum and minimum coalesce to the point. This is the degenerate point. Then if you go through that point like that, so you see, first you have this, and then you have this, which is x4. And then you have this. And then everything was done what is in fact necessary. On other side is the down. You see, then you have this this down there. I mean, this is the same like this one, but for minima, which is x4. And then, because this is 3 dimensions, and the surface in 4 dimensions, a 3-dimensional surface in 4 dimensions, then there is its intersection by the plane u1 equal uvw by u equal constants, and that's look like that, this surface. And its projection gives this. There are such singularities. So you see, this is just, I have to speed up a bit. If you try to, it's better, in fact, it's better to have everything together than just move sometimes. You see? Our brain takes it all at one moment. That's okay. Do you understand that? Yeah, this is just the calculation. I mean, drawing these potentials for different points of U. Butterfly. Butterfly has even look. But the butterfly is more complicated because it's in 4 dimensions. So this is the more complicated situation. This is only this set, which is looking like butterfly, is intersection of the critical set. Swallowtail was a full critical set, but butterfly is an intersection of the full. We are not able to draw this set in 4 dimensions, 3-dimensional set. Usually we by intersections, by we don't see in 4 dimensions. We see in 3 dimensions. But we can see in 4 dimensions, but in different way. I mean, that's physics always says, because we dynamics. No, that's not this. And then, you see, this is some computer generated this butterfly, but this is true one is looking like that. It's my garden. That's also nice. And now the scientific approach. What for we use this? You see, you normally if you try to understand some phenomena, you can just got new. You've got new computer, or maybe not computer, but maybe new car. Another car. You got new car, and you want to. And then in the beginning, if you don't know what is this, there's a black box. Black box. So Dirac mentioned in his book that the quantum physics is a black box. This was stopped to understanding the quantum physics long time. The Nobel Prize winners are just something after so many years. Okay, the scientific approach to each phenomena, our approach looks like that. This phenomena and the object is a kind of black box. We don't understand it. We don't know much about that. We see something that there is. We distinguish it as a something what we are interested in, but how to investigate? Well, yes. So we see that there are some parameters, some influence we can have on the system. We can have some influence, and then look on the response of the system. So there are parameters of the response, so internal we call parameters, and the parameters of influence. Oh, like for example, you have the you boil water. So you make temperature, you change temperature, you may regulate temperature. And then you see in the water what is boiling at one moment. So this is internal parameter, this boiling of water. After some time, it's no anymore water, but it's gas, it's vapor. Everything was vapor. So then this is this X. So there is, so usually it's like that. We have sometimes there's spins, sometimes there are some other objects. Sometimes this one also whatever you can do. You can change the pressure. You can put the particles with some energy. So there's also the energy you can supply, and so on and so on. But then, if you know system when you say system, if you find a relation between U and X, well, that's just if you know all responses for U which you apply, you know the system. Of course, we forgot, but sometimes we know other people. You meet some new colleague, yeah, and this is black box. Nevertheless, you see how it looks like. They have nose, header, but still it's a black box. If you tell something, you don't know what's the response. So you have to discuss a long time to know somebody. Ask all questions and wait for responses. And this is exactly relation between your questions and his responses. If you have all responses for your all questions, you know the person. You know the system. There's no any more black box. what? Yeah. Yes, but this is true. Whatever very wise people say, this is just true. And now elements of how to make models of using our theory, elementary. I started about a relationship, yeah, relationship that you met somebody, and you know if you want to know him or her, you have to ask all possible questions and get all possible answers, even if they are false. That's doesn't matter. This is his response. And the models which are done by so-called catastrophe, classical catastrophe, or this theorem which I showed, they are very, very natural. I mean, it's necessary to distinguish in the system, if you see the system, something what is not on what you have influence, some parameters which you can change, and some parameters which you cannot change. For example, if you have relation with some you have boyfriend. So you met some guy and you maybe better you now, because from the point of view of girl, I'm not so good in this stuff. but maybe from the boy. So you met a girl, and this is your girlfriend, for example. So what you want from your girlfriend? Now, at first, you want that she accepts you. Acceptance, the parameter which is acceptance. Parameter acceptance is just this one, X level of acceptance. Here, if you are here, she accepts you very much. If you are here, she rejects you. She doesn't want you anymore. And never see you again. I was, of course, I exaggerate. So this is X. This is this. You can, the numbers, you can, of course, parameterize by numbers, but you have to, but at least you can make it, say that sometimes she accepts you less, more, and more. That is possible to do this. And what kind of, and on that parameter, you have no influence, just like say, oh, accept me, and she accepts you. No, it is the result of some interaction. So where you are on that parameter is a result of something, your deep interaction. Okay, so then you have some influence. You have influence on these parameters. Mental comfort, psychological comfort, which you can give her, and material comfort. Of course, if you ask why not other parameters, of course you can take other parameters. But the problem is, if you look, what is most important? Most important in a relation is that that the couple have some material conditions to meet, to be together, have some apartment or maybe some room and some something to eat, some work, This is material comfort. Another point which you have as a boyfriend have influence is a comfort, is a mental comfort, means here this is psychological, that you sometimes bring her flowers, you tell her that you love her, you understand? Yeah, this is just something like that. Maybe not even tell love, but maybe you say that she's a beautiful girl, or maybe that you like her, not necessarily love, and then maybe every day, maybe every hour, maybe every hour. So then you change these parameters. You understand? Yeah. So then you have the process here. One process here. But you say, we might say, why? But so terrible number of girls which are so different. The girls are so different. Yes. So let's take two different types of girls. One, girls are very materialistic. So think only about to have money and a lot of dresses and so beautiful. Okay, but it's okay. Why not? Other girls are idealistic. Oh, they think that's for me most important. That he loves me. That we understand each other. Something what is we call idealistic. Some things. So the two models, one is idealist, and then materialist. So on the end of the interval, relatively far away, but that's so acceptable. Don't worry. I have nothing against materialist and idealist. So let's take idealist first. So then we build the model. We put like that, and we see and we check on the point where this is working well. So if we take some point here, so B is big one. So there is a big material comfort. Big material comfort, you see, what I'm, A is material comfort. Yeah, mental comfort. A is mental comfort. Yeah, you see? A is mental comfort, mental comfort. Then you are here, so you are high on X, so she accepts you. And there is relatively, B is relatively also big, material comfort. And then, you see, you are just, you have very good material comfort in the couple. But you forget about mental, about psychological. You stop to give her flowers or say her nice things. And then you see the process is going there, but keeps B constant. So material is okay. You have good job. You always finance everything in the couple, yeah. And then, but A is going down. And then she rejects you at some moment. It's a catastrophe, rejects you. Doesn't matter, you are fired. For sure. Jumps here, this is a rejection because this is somewhere X here. So what happened? What then? Nothing, they just reject. Then it's possible only, maybe it's impossible to go this way because it's hysteresis, so that's impossible. But you can, of course, go this way maybe. So just separation, you just separate for some time, you understand. You go to Switzerland, she goes to Brazil, and for some time you are outside. And then you are going this way, process going this way, this way, this way, and maybe you come here after some time, if you come again together. It happens. But now take materialists. What is, there's a question. Model should be different because the person is different. Of course, I only turn around this surface, you see? Now here is A and B. Before was A, B. I change variables because of course there are some extremal differences. In between, there is between, you know. For extremal, it's much easier to take models. And then you see you have similar situation but different different reactions. You have materialis. So you see you are here. There's comfort. This is A mental comfort here. Mental comfort is I should no, so before for idealist. You see, idealist, if you change the mental, I mean psychological was rejection. But if you change B is going to 0. So material comfort is less, then never she rejects you. If you keep A, because if A is positive here, you see, of course, she will accept you less, a bit less, but always positive. Always positive. This is idealist. You are fired from your job. You have no money at all, and even she will keep you if she has some money. But heaven never rejects. And the model again opposite for materialist is the same, but opposite. Opposite. You see, yes. You see. Now, if you B is a material comfort. So if you have material comfort here very high, A is mental comfort, and then material comfort is going down. You see, always you give flowers and so on, and you give her, you say her that you love her, but nevertheless you have lost the job and you have no money. Then she rejects you. B came to that point. B is material comfort. So she is this comfort, material comfort for her is too small. So she rejects you. But if you say a big material comfort B, but mental comfort is going down. So this psychological, you just ignore her. I mean, then no, she's still with you, like before the previous one. Of course, it's accepting a bit more or less, but still accept. No catastrophe, no continuous change in this direction. Very interesting. And you can make more models, and even those one check on other processes using computer. You can just predict sometimes behavior of the people, even in such trivial models. people are not so complicated in some level. In some level, the psychologists, they know. And then, of course, here is also the processes. You see, we call it as a butterfly effect, some people say, yeah, something that non-linear effect that some butterfly moves with somewhere in Brazil, and then here we have bad weather. That's a different story. This is how much is true, but this is non-linear effect and stability. And then you see if couple meet there, then somewhere, then the comfort, both mental and material, are very small here because close to zero. So if you meet only person, then you see how it looks like. Well, dressed just normally, smiling or not smiling, such very, very small things you observe. You don't know much. But for materialists take into account something different than idealist. So materialist looks on her, on him, girl, and so his dress is too old. Some holes on the somewhere, you know, something already. So then she moved a bit on here, a bit only. And then if parameter I is growing, that means a mental. So the guy wants to invite her to the cinema or something to know each other. Then this parameter is growing, so this process. But she rejects him from the beginning. But this was result of very small, very tiny decision here. Very tiny decision. This is terrible life, you know, that people have no chance to avoid such tiny decisions, which might cause very serious results. But this is life, unfortunately. If she knew that, she has that guy had a gold watch. She noticed this. Well, that's not especially. I also like gold watch with some of her. That's not. But then move there. But then he invites her to cinema, theater, and then of course she accepts. But it might appear that that guy was a proper for her, whom she rejected. Such terrible life, you know, maybe. Now, anyway, this is so many divorces and so on. The same with idealists, but reacts different way. Okay, free choice and so on. Oh, there's a very nice realization of this synonym in caustics. You see, I have, you know what is this? This is the mug or cup, which is empty, and this is my photo. And on the bottom, you see, in the bottom, this is those caustic, and the light is somewhere. Then the rays reflected from the boundary of the mug gives you such. But this is exactly our bifurcation set. This one. This is that, which is stable. So if you have, what is more even important, if you have elastic thing like that, and you put those light, no. I see. You want to see? Then look. You see? But even if I move, that's not enough. Even if I do this. So that's just stability, visible in experiment. That's it. What to say more? So it's everywhere. And of course, the explanation for that is like that these rays are, you see, coming, reflected, and this is envelope of rays. They are focusing, gliding on such curve of our curve. Yeah, and that's also the other explanation. The same phenomena. If the source of light is if you have here the source of light, then you have such phenomena, of course, if this is transparent in some sense. This is mathematical more than physical. And also, that what we see is this one. This one is invisible because is protected by the wall by this one. So light is going this way. So that one, so we see, but that one we don't see. But there is. If we open our mathematical eyes, then we see everything. Physicists are sometimes blind. But that's, of course, this is very interesting for the caustics for the ellipse. This is simple to generate now, having this simple Mathematica or something. So this is why it's not big achievement. Sometimes ago it was achievement. Okay, and then explanation of energy of that. You see, if you take the two parallel rays, then the partial of energy, the quantum of energy is going there. But this is it's in the space, which is smaller and smaller and smaller and smaller, and this is focusing and lightning. You know this phenomena. So this energy focusing. And then it looks like that. I show also some process in the moment. So the caustics, and mathematically it looks like that. We have just the surface made of all rays. Space of all lines, oriented lines in free space is 4-dimensional. It's an exercise at home. Check that the space of all lines, oriented lines in 3 dimensions is 4-dimensional space. Moreover, it is even might have some structure. This is some cotangent boundary to sphere, to 2 sphere. But that's students who are ambitious, they very easy to calculate. Anyway, these lines, they build a surface, 2-dimensional surface in 4 dimensions, and then its projection on to space on the bottom of the cup gives this red line. And the rays are invisible, usually rays, because rays are instantaneous move of the photons. Of course, wavefront is moving. This is the wavefront which is moving here, and then wavefront has singularities on this caustic. This is very simple, but I have no time, so I have to go quickly further. I have still some time, but not so much. And then symmetric caustics is beautiful. This is some really great knowledge to know, and then investigations, and then symmetric caustics. And then evolutions of caustics is made of some other people, Arnold and other people. And this is just the evolution on the droplet, which I studied a long time and with my colleagues. And also the caustics in diffraction. In diffraction also I studied these caustics. These are very beautiful caustics, different looking. These are just connected with singularities on boundaries, which I taught you yesterday. Evolution of caustics, all the types. Arnold classified that. And caustics, there are envelopes of ray systems, and that's it. That's it, like that. If there is any symmetry, then of course the caustics are also symmetric, and so on. You see? These are and then caustic and the wavefronts are moving singularities of wavefronts. The singularities of wavefronts are just these guys. These are singularities of wavefronts, and they are moving on caustic. No, this is just technology. And then maybe for today, the concept of the present is a big wavefront, and the past and future, and between is a big wavefront. And then, of course, we call it frontal. We call it frontal if there is the time, exists time, which is the vector field which is defined on the surface. We call it frontal. Frontal, of course, is defined precisely in a bit more precise way, but I don't want to say here. And then, of course, shock waves are giving the hyperbolic umbilic. Oh, this is how, if this is surfing, people who surf, you know, the wavefront, not wavefront, but the wave on the sea is the, you know, turbulence from some moment starting. At this point here is the hyperbolic umbilic. Yeah. And then, of course, surfing, people who are surfing, they know they should be here. No, here they will be, of course, covered. Here, then they are not going to go further. I mean, because they jump on the other side. So they know very well what is hyperbolic umbilic. And then visible contours. You see, if you are in mountains, you see like that. You are here. Some guy, some with mustache. So then you see this mountain. Then this guy see mountain like that. Yeah, that's obvious. But this one, you know, part of this mountain is covered by this one. So he doesn't see this because he is not mathematician. If he is mathematician, he knows this. He see this, and then he also see this. He knows this. And he knows that all this stuff is a beautiful swallowtail. That's it. But if he is not mathematician, he doesn't see this. He only says maybe the wind, nice, sun is fine. We know much more. We see much more. Of course. And now the last moment. I want to show something. Just a few minutes. Just few minutes, okay? Listen, if someone oh, now I will ask questions for everybody, also you. What do you see? Ah, she went there. What do you see? I mean, face, yeah, face. Ask people if they see something different. They have the reply. and then what do you see now? Still, no? Different face. Different face. Also different face? Ah, different face. Different face. And then here's different face. Ah, you see, somewhere here you should see the woman after bath. You see, and some because you are the girl, so you dance. But boys, they very quickly see the woman here. So you see, this is the perception. If you go the other way, let's go other way. You go the other way. Of course, now you know what is this. But if people does not know, then if you go the other way, oh, he was not here. So maybe he's but Tao, look, what you see here. Woman, okay, absolutely, you are a healthy guy. What you see here? Well, I don't know, what do you say? No, if you saw here woman, then the next one is quite similar, no? So say that woman. I would see woman. Yeah, I also would see woman. He also woman. Some people see everywhere with boys. Some boys everywhere say they see girl. But that's healthy. Don't worry. And then that's girl. Also, I see girl. Even here I see girl, but here I don't see girl. I mean, I see girl, but I decide no, there's something strange. Maybe face, maybe some potato or something. You see, the eyes was a strange, nose, and so on. And then and that's just multiplicity of perception. In our brain, all the time we have such multiplicity, these catastrophes. So there are some jumps coming somewhere here on that, and then you have this picture Yeah. I show the picture and that's it. And then you have such picture. The presentation. This is just the last moment. Why I switched off this completely? That was mistake. Oh, you see, that's what I showing. Yes, and then you get this one. But the red line is the set where you have this change of perception. What is this? What kind of parameter this is? This is a complexity. This is a complexity. You see, you have here not very complex. You have not much paint in some sense. You have more details, more details. So this is details parameters, more details. If there is more details, then there's a big, this distance of the perception. If less details, then you see all the time the same. That's natural. But this parameter is very interesting, you know. If you have more knowledge, you see more objects different. If you have less knowledge, you have everything the same. I mean, that's also natural. So you see, this. If you go this way, you have perception here. You have jump. If you go from girl, you have here, and then if you have less, then you are the same almost. You are the same. Thank you very much. Thank you. Tomorrow about singularities, Mathematica. Thank you. In fact. Yes, of course.